Hello folks, and welcome to the channel, or welcome back. Now in the past I've made a lot of videos about ignition systems, and this is going to be the first lesson, and it's going to be about the ignition system. Now I don't know if this is of interest to you, but have a look at it and please comment and let me know if you like this or not. And if you don't like it, then I'll stop doing it, stop wasting my time on it. But if you do like it, then I will continue and create some more sessions or lessons on different topics, besides all the other videos that will continue. So, without any further ado, let's start with the ignition system. Hi there, my name is Steve, and I'm an electronics engineer. I'm also known as D3S Shooter on YouTube, and D3S stands for a specific model of Nikon cameras, as I used to shoot with cameras of Nikon, hence the name D3S Shooter. I have a long story and history on race cars and classic cars, mechanical work and electronics work, and I'm happy to share that information with you for whatever it is worth. So here are the topics we're going to discuss, and we will focus on a 4-stroke gasoline combustion engine. So why do we need ignition? How does it work? And then we'll be looking at some tuning and fault finding. We are not going to cover coilovers and ECUs, nor will we cover multipoint or magneto and trembler coils in this session. Now, before we dig into the actual ignition system itself, we'll do a little refresher on a 4-stroke gasoline combustion engine. As you can see in the picture, we have all the different elements, although I'm quite sure that most of you know exactly what this is, but nevertheless, I will take you through a short introduction on how a 4-stroke engine is working. We have 4 strokes: intake, compression, labor, and exhaust. And we know that the crankshaft is rotating twice 360 degrees to complete the 4 strokes. Our first cycle is what we call the intake cycle. And during that cycle, the piston is going downwards inside the cylinder and creates a vacuum. And of course, we'll have to get an air and fuel mixture into the cylinder, and this is happening through the inlet valve, which is opening up. The 2 points on the piston are called top dead center and bottom dead center. During that moment of the intake, the inlet valve opens up as soon as the piston goes down and closes as soon as the piston is at its bottom dead center. It is important that the exhaust valve stays closed during the complete intake cycle in order to assure a proper vacuum inside the cylinder. The opening and closing of the valves is controlled by the camshaft, and the camshaft is driven by the crankshaft. Timing is of the utmost importance, and we will discuss this later in the video. When the piston has reached its bottom dead center, the intake valve is either closed or is closing. The piston then travels back upwards, and we call this the compression stroke, compressing the air and fuel mixture. Once the piston is near its top dead center, we're getting ignition. The spark plug ignites the mixture, and that makes the beginning of an explosion and starts the labor stroke. As with any explosion, the combustion causes a tremendous force onto the piston and forces the piston downwards, hereby rotating the crankshaft. The force is expressed in horsepower and converted on the crankshaft to what we call torque. During this moment in time, both intake and exhaust valves must be closed. Now that the labor stroke is complete, we must vacate the cylinder from the exhaust gases, and thereby the piston moves upwards, the exhaust valve opens up, and the gases are extracted through the exhaust manifold. And the cycle repeats. We have again an intake cycle, piston is going down, then the piston is going back up, we get our compression cycle, both valves are closed, we get ignition. Once we have ignition, the piston is forced violently down, we call this the labor stroke, And then when the piston have reached its bottom dead center, it's going to move back upwards and extracts the fumes from the cylinder through the exhaust valve, and the cycle completes. Now that we know on how the four-stroke engine is working, we need to determine at what moment in time we need to ignite the air-fuel mixture. We know already that it's the end of the compression stroke, but at exactly how many degrees before top dead center has this to happen? And that is subject to many different parameters. So let's have a look on that. So the right moment of ignition depends on many different factors. For instance, the type of fuel. Not all fuels are burning the same way. Think about diesel fuel versus alcohol. What burns faster? RPMs. Well, the faster the engine is running, maybe the more advance we have to give it, because the piston is traveling a further distance in degrees within the same given time as what it would do on a lower RPM rate. What about the compression ratio? High compression ratios, lower compression ratios. Very important, because the air and gas and molecules will be closer to each other or further away, so the flame propagation will be different. Now what about the air-fuel mixture? The AFR. Sometimes we run lean, sometimes we run rich. Again, we need to consider this for the ignition moment. And then we have the temperature of the engine, which also has a huge influence on the moment of ignition. And I'm quite sure that some of you that are into racing, you probably had self-combustion at one moment in time and it blew up your engine, most likely because of a very high temperature inside the cylinder that was igniting the fuel mixture at the wrong time. And there are some other parameters that are of importance as well, but we'll look at the most important ones. Let me give you one example. On the graph you see a red line, we call this fuel B, and you see a black line, which we call fuel A. So now we have two curves, a black curve and a red curve. Fuel B is a fuel with a low flame propagation, so the flame is not building very quickly up throughout the mixture. And fuel A has a fast burning time. So on the bottom of the graph we have our time, and vertically we have the flame propagation. So if we take both fuels and we ignite them both at the same time, then you will see that fuel A will reach its peak in burning much faster than fuel B. This could be an example of an alcohol fuel versus a gasoline fuel. But don't worry about this, we come back to this. But that already gives you a hint on why ignition is important, depending on what fuel your engine is going to run. Factors that can influence your ignition will be discussed further down in the video. But right now, we need to see on how we are going to create the spark. And once we created the spark, at the right moment in time, we will have to distribute the spark. We may not have a single cylinder car, we may have a 4-cylinder, a 2-cylinder, an 8 or a 6 or a 3-cylinder. So it's important that we are able to distribute the spark to the proper spark plug and the proper cylinder. So here we have a very simple diagram of an induction system. So we have what we call a coil, and you can see on the right hand side on the picture we have different types of coils. They come in all forms, and the coil itself is nothing more than a transformer. It has a primary winding and it has a secondary winding. When the contact is closed, we will have a low voltage and high current flowing from the plus of the battery through the primary winding back to the ground. That is building up a magnetic field inside the induction coil. The moment we break the low voltage high current path, there is going to be an induction on the secondary winding. Now the secondary winding is typically consisting of a lot of windings on thinner wire, and the primary winding is having a thicker wire and less windings, and the result is that we are having an induction to the secondary winding which is going to cause a high voltage between 10 and 20 kilovolts, but low current. And that we can use to ignite the spark on the spark plug. Now we know that we must be able to interrupt the current through the primary winding of the high tension coil in order to create the spark. And therefore we will need some type of a switch. Now I call this the contact point. If you worked on cars before, especially older cars, then we call this the breaker points, and I'm quite sure you have been adjusting the gap on those. So whenever the breaker points or the contact point opens up, the current stops through the primary winding, we get induction in the secondary winding, and we develop a high voltage on the secondary winding. That high voltage is then passed along to the distributor, and inside the distributor cap we have a rotor which is pointing to the right lead, and then the lead connects to the spark plug, and then we have the spark on the spark plug itself. It's important to note that the high tension coil comes in two flavors. We have what we call a low impedance high tension coil and a high impedance high tension coil. And you can see the resistance values for primary and secondary windings in the little table that we have there. What is important here is that if you are going to order a low impedance high tension coil, you must use a shunt resistor. Otherwise, you may burn out the primary winding. The shunt resistor will reduce the amount of current that will flow through the primary winding. On the other hand, if you're going to use a high impedance coil, then there is no need for a shunt resistor at all. So keep that in mind. Typically, the low impedance HTCs were used on older cars, but modern cars, they tend to have a high impedance HT. We have here a few examples of contact points, but there are more types. On the bottom we have our well-known mechanical type, the breaker points. Then we have the inductive Hall version, which is no longer mechanical, but is based on induction. And then on the right hand side we have something what we call special, the twin, special with two breaker points. Now there are other types like optocouplers and so on. On the left hand side we've got a picture of a traditional distributor, and the 2 points of interest for us right now are the notch and the contact breaker points. The notch is driven typically by the camshaft. If you have a 4-cylinder distributor, then you will see 4 notches on that shaft. If it's a 6-cylinder, you have 6 notches and so on. We all already know that if the contact breaker points are closed, we get current through the HTC primary winding. And while the notch shaft is rotating, the contact breaker points will open up. If they open up, we get induction, we get high voltage, and we get a spark. While the notch continues to rotate, we will see that the breaker points will close, and at that moment in time we are having current flowing through the primary winding of the HTC. So it is really the notch that opens and closes the contact point. That is why it's so important that we adjust the breaker points with the right gap, because that is going to define the dwell angle. Now the dwell angle is a fancy word, but it's nothing more than the amount of degrees under which the contact point is closed. This is very critical because we need to allow sufficient current and time to flow through the primary winding of the HTC to build up a strong magnetic field. If the dwell angle is too small, then we will not have sufficient buildup of the magnetic field, and we will have a poor induction, and we have a low high tension voltage, and as a result a poor spark. So the traditional mechanical breaker points have been replaced by electronic solutions, and we'll be looking at 2 types: the capacitor discharge ignition system and the electronic ignition system. But regardless of which one we have, we do require to have a pickup point, a replacement for our well-known breaker points. Typically, the pickup point is either a Hall effect or a magnetic pickup, but it could also be a optocoupler. That device will then generate a pulse each time it is triggered, and then the pulse is then fed to either the CDI or the electronic ignition system. If you are using an electronic ignition system, then that pulse will be amplified by solid-state devices inside the ignition system to drive a high current through the primary winding of the HTC. A CDI is working slightly different. It's going to load up a large capacitor inside the CDI, and this capacitor will discharge across the HTC as soon as it receives the pickup pulse from the pickup device. Now be very careful, as the CDI is using a high current and hundreds of volts on its primary winding to the HTC. So we've been able to generate a high tension, and that could result in a spark, but somehow we need to get this high tension to the proper spark plug. And our engine might be a 4-cylinder, a 6-cylinder, an 8-cylinder, and it might have a certain firing order, maybe cylinder 1 first, then cylinder number 3, then cylinder number 2, and then 4. Firing orders could be different depending on the engine. So somehow we need to have what we call a distribution system, and that is why we have what we call a distributor. The distributor typically is driven by the camshaft, and it has inside the pickup points, be it mechanical or electronic. And then on top of it, you will find the distributor cap. And on the distributor cap, you have always a central point. And on the central point, we connect the lead coming from the high tension coil. That central point will then distribute the high voltage to one of the other connectors on the distribution cap. And each connector there, all around in a circle, will actually lead up to a specific cylinder. Inside the distributor cap, you will find a rotor. And on the central point on the rotor, we will actually have the high voltage coming into, typically with a carbon little spring pushed part. That often goes wrong, so we might talk about this later when we start talking about troubleshooting. And then the rotor will then distribute over the brass pathway to the proper lead or the proper connection point on the distributor cap. Remember that the rotor will rotate in a very specific rotation direction, either clockwise or counterclockwise, and that we have to make sure that we do connect the spark plug cables in the right way so that we have the right firing order sequence. But we'll talk more about this later. But the main point here is that we need to have a distributor with a distributor cap, and inside the distributor cap we have a rotor which is going to distribute the high voltage to the proper spark plug. There's one more component we need to talk about, and those are the spark plugs, and they come either as cold or warm types and anything in between. And the little table that you have on the screen is typically for an NGK spark plug, and they have a code. The code is a BP6ES11, and it's just an example, and every digit has a meaning. So we are really interested in the third digit, the 6. And the 6 is indicating the heat range. Now, cold types have typically a large insulator jacket surrounding the electrode, so they convey the heat to the engine block much better. And that means that the spark plug itself is not going to get real hot. That is good. But the problem with that is that we're going to have an issue on idle because it's going to spoil the electrode, because we will have carbon buildup and so on, and we won't be able to burn it off because the spark plug isn't getting hot enough. On the other hand, the cold type is good, especially if you go in high RPMs and you develop a lot of heat on the car. Then they are really good, because if you were to use a warm type, then you probably may melt down the electrode. The warm types are just the opposite. They have a smaller insulation jacket, so the electrodes are getting a lot more hotter inside the engine when the engine is running. So they are conveying less heat to the engine block, which is really good for running idle because then they will burn off all the deposits on the electrode. But on the other hand, if we're going to go on high demands and high RPMs, then they won't be able to sustain that, because what will happen is they actually will get so hot that they are going to melt down the electrode. So we really need to make sure that we select the right spark plugs with the correct heat range, because that is all very critical. And if we don't do this right, then you may run into some serious problems with your engine. Now, in general, you will find the specs for your engine in the technical manual of your specific car. Which one should we now select? So now the question is, what should we use for our car? Cold or warm spark plugs? Well, the answer to that one depends on many different factors. It's the engine power, it's the compression, the fuel type, and how you're going to use the car. Be it a street car, a race car, or a fast road car, it all depends. But in general, we can say that engines that are running at a high RPM, with high compression, are better off with colder types, and engines that are running lower RPMs and low compression are better off with warmer types. And now the question is, why? So maybe you can now formulate the answer. I assume that you already got the answer right, but let's recap anyway, as I kind of alluded to it in the previous slide anyhow. So on performance engines, those are engines with a high RPM and a high compression. They are much better off using a colder spark plug. And that's very simple because those engines are creating high temperatures inside the combustion chambers. And that can cause a too hot spark to glow and trigger pre-ignition on the fuel air mixture. And that is devastating for an engine. If you're running at high RPMs and this is happening, you get an unwanted ignition, and that could be at the right time or at the wrong time. If it's at the wrong time, it's going to blow up your engine. So often we call this pinging, and that is the same as murder of the engine or damage to the engine. A too cold spark plug, however, will fall at low RPM because the deposits on the electrode will not burn off. Now, standard engines are engines with a normal RPM and a relative low compression. They are better off using a hotter spark plug since the temperatures are lower inside the combustion chamber. And if you were to use a cold spark plug, it will actually be fault. And the hot spark plug will actually burn off that fault electrode, but not if you were using a cold spark plug. So folks, so far so good, and I hope you are still following and didn't fall asleep yet. I know it can be pretty boring sometimes, but now we need to talk about the ignition moment. What is the right time to deliver that spark to the spark plug? And that depends on many different factors. The RPM, the mixture, the fuel type, the temperature, the compression, and a couple of other factors. And we need to fix all this. So how are we going to solve this so that our ignition system is adapting to all these different parameters? Folks, let's have a look on the effect on the ignition moment and RPMs. And this slide might be a little bit complicated, but I will try to explain it. So we have on the vertical axis the flame propagation, and horizontal we have the time. Now you can see the curve inside the graph, and the curve reflects the burn time or the burn behavior of a specific fuel. And the trick is in any engine that we have the peak of this curve just at the top, that center. So we benefit from the maximum power of that explosion or that combustion. If that peak is coming after the top, that center, then we are going to lose power. And if the peak is coming too early before the top, that center, then We have another problem. Then we start getting into a pinging problem because that peak will actually try to push down the piston while the piston is still going up in its compression stroke. So somehow we need to make sure that the engine is running properly on idle, low RPMs, and in high RPMs. And we will need to do this by adjusting the moment of ignition, and often we call this the advance. So now let's assume that the engine is running on idle and we have set our ignition advance to, let's say, 4 degrees or 5 degrees. So the piston is moving at a slow speed inside the cylinder, and we have the ignition moment just at the top dead center, so in fact 4 degrees before top dead center, which is matching up with the peak of the burning curve or the flame propagation. Now let's assume that we are going up in higher RPM, so the piston is now moving a lot faster inside the cylinder, so it's going to reach a lot earlier at top dead center. And as a result, the peak, which is still having its own burning time, will come much later after top dead center. So now we have lost a lot of power. So it's important for us that we can adjust the ignition advance so that it works under all RPM conditions. The solution is rather simple. Inside the distributor we have what we call bob weights, and those bob weights, they will fly out under the centrifugal force while the shaft is spinning. There's also some springs that will retract them back or limit the advance. If the bob weights move out, we are having more advance. Bob weights are mounted on the shaft of the distributor, and while the distributor shaft is rotating around, the bob weights will be thrown outwards by the centrifugal force. They are a bit constrained by the springs, and as such they will move forward the advance. So in other words, they rotate the platform where the pickup point is, and we get more advance. If the RPMs are coming down, then the bob weights are retracting again and the platform rotates in the other direction and we have less advance. If you are into tuning your car and you want to influence the ignition curve, then you can work on the springs. You can install softer springs so you will have far more advance. You can install harder springs so you have less advance. And of course you could also play with the weight of the bob weights. Now on modern cars you can do this with a program, and quite often the distributor will allow you to program it through a USB or a Bluetooth interface where you can set your own ignition curve. So let us have a look on one of those curves, and that's a typical curve that you would find on a 1, 2, 3 ignition system where you can actually program that curve. So that is not based on those bob weights and springs. It's fully electronic. So there are different flavors of adjustment. Now let's take it a step further. We need to look at our AFR, air-fuel ratio, and the advance, because lean mixtures are burning slower and rich normal mixtures are burning faster. I know that this is a fairly busy slide, but we'll take it piece by piece. So assuming now that we are going downhill or we are cruising along, then our throttle on our carburetor will be either fully closed or partially closed. And at that moment in time, we are having a very lean mixture inside the cylinders, and we know that the lean mixture is burning slower. So the peak is coming later, but we still want to develop enough power to keep the car moving, especially under cruising conditions. So we need to advance the ignition moment even more, further than what the bob weights are doing, and therefore we are using what we call the vacuum advance. And the vacuum advance is the vacuum out of the intake manifold, which is fed to the side of the carburetor, and there we have a little membrane that will pull the bob weights even further, or that platform even further, so we get more advance. Of course, if the throttle is open, that advance isn't working anymore because the vacuum falls away and we fully rely on the bob weights. So under normal driving conditions or a normal rich mixture, for instance under acceleration, or we are going wide open on the throttle, or we are giving enough throttle, then the throttle is open or partially open to a large extent, and at that moment in time, the vacuum disappears completely and we fully rely on the bob weight advance. That is why in racing, we never have a vacuum hose or a vacuum advance, because we are most of the time wide open. We are always running normal and rich. We never end up in the lean condition. Anyhow, if you look on the diagram or the curve that we have on the screen, it's the combined advance. As I explained, so the blue curve is how the advance system is working only with the bob weights. So whenever the throttle on the carburetor is open, we fully rely on the centrifugal force of the bob weights creating the advance. However, if we ending up in a lean condition, for instance, we let the throttle go and the butterfly closes in the carburetor, then we want to continue to have some power, like under cruising, and we need to make sure that we get more advance because that leaner mixture is now burning slower, and that's the moment in time the vacuum advance will kick in, because we have created a lot of vacuum inside the intake manifold, which will rotate the advance inside the distributor, and that is the green line, which is the combination of the bob weights and the vacuum advance. Remember, even though we have vacuum advance, the engine is still running at a certain RPM, so the bob weights are still doing their thing. This is a very easy slide compared to the previous one, and we are looking down onto the vacuum advance mechanism. You will see the distributor, and on the distributor we have a vacuum advance membrane, and the blue arrow is connecting the vacuum membrane towards the intake manifold with a small tube, and that's where we apply the vacuum. When the vacuum is applied, you can see with the black arrow that we are moving forward or backward the complete platform inside the distributor to create that additional vacuum advance. In this little video I have hooked up a vacuum meter, and I can see the vacuum being created in the intake manifold depending on the throttle position. So now we need to talk about something very important, the effect of the compression on the burning speed. So if we're looking at a low compression engine or an engine with a very low compression ratio, then the burning chamber is fairly large. That means that during the compression stroke, the air and gasoline molecules are far away from each other, and it makes it very hard for the flame to propagate through that kind of a mixture. So it's going to burn a lot slower. Now, on the other hand, if we are having a high compression ratio and a very small compression chamber, then these air and gas molecules, they are so close to each other that they will enhance the flame propagation when it starts burning. So we're going to get a lot more power out of that one. That all has, of course, an immediate effect on how much advance we have to give to the engine, and that's different for a low compression versus a high compression engine. So let us talk now a little bit about fuel octane. Octane is a number that is given to a specific gasoline, and it gives you an indication on how stable the fuel is in terms of self-ignition or self-combustion. The higher the octane number, the more stable the fuel is, so you're not going to run the risk in self-ignition, which you may have with lower octane fuels. This can be very dangerous. You can get into a pinging condition or a knocking condition, which is, as I said, very dangerous, and it will either destroy your engine or it will cause serious damage to your engine. So it's important that you have the right octane on your fuel, and the octane will also relate to your ignition system. It's a common misunderstanding that a high octane fuel like 102 is going to provide more power. It does not. That depends on the blend of the fuel, what is inside the fuel. Gasoline is often mixed with other products. That will affect the power that it's going to produce, but it's not the octane value. Temperature is a very critical element, and I'm having here just a blowtorch, and as you can see I'm just feeding gas in initially, so it's a very rich mixture, and then I'm adding slowly oxygen to it, and you can see how the flame is changing from yellow to blue. That means the flame is now getting hotter, and the mixture is now getting leaner. So the point here is that lean mixtures are increasing the engine temperature inside the combustion chamber. And that, of course, has an immediate effect on the flame rate, on the burning rate of that fuel. That fuel will burn faster, so we need to compensate with the ignition for that. Furthermore, depending how your car is running, your ignition system will have to have the proper spark plugs. We have spark plugs in all kind of types and degrees of heat, so we have hot spark plugs, colder spark plugs, and you will have to fit the proper spark plug accordingly to how hot your engine is running. What you're about to see is on how I adjust my ignition system. I like to keep things simple and straightforward, and adjusting the ignition consists of two steps. It's the static adjustment and a dynamic adjustment. And to be very honest, the best tools are your ears and eyes. If you ever met a very old mechanic, you will see he's not going to use any of all these fancy tools. He's just going to listen and look at the engine. And this is how he's going to adjust the ignition and the ignition advance. So before we start adjusting the ignition, there is a couple of pre-checks we must do, otherwise it doesn't make sense to adjust the ignition at all. The first thing is to make sure that you have the correct spark plugs and that the electrode gap is set properly. Quite often that is something like 0.7 millimeters. The next step is to make sure that the high tension coil cables, the cables between the distributor and the spark plugs, have no damage and are properly installed. Third, making sure that the engine has a good ground. Quite often I've seen problems with grounding the engine, and as such the spark on the spark plug is not going to work too well. Fourth, the distributor. Check for cracks, signs of short circuiting, and making sure that the central point, spring, is not having too much wear. Remember when I mentioned that there is a carbon tip inside the distributor that points towards the rotor? That often is in a bad condition, so always check that one. Then we have the rotor. Make sure it's clean, no cracks, and that it has the correct distance to the contact points of each individual cylinder in the distributor. Make sure that you have the right compression on all cylinders and there is little variance between the cylinders. Making sure that the valve clearance is set correctly, that the fuel and the carburetor are set up properly and adjusted, that you're running good new fuel, not old fuel which has been sitting there for 2 years. Making sure that you have fresh fuel. Check that the vacuum system has no leaks, that it has good hoses and there is a proper suction. This you can check with a vacuum meter. And then finally, making sure that you have good contact points and a capacitor, that there is no burning on the points. And that of course is only if you are using those old-fashioned contact breaker points. Once you've done all this, you're ready to start to adjust the static advance. So here's the sequence on how I adjust my ignition system. You do this with a warm engine, of course, and we have done the pre-checks. So the first thing I do is adjusting the breaker points gap. Of course, if you have breaker points. If you don't have any, then you can't do this. Then we proceed to the static adjustment. I'm setting the timing on the distributor, but the engine is not running. And we'll look on that in a few minutes. Once that is completed, I will crank up the engine. I will let the engine run at idle, and I call this dynamic adjustment at idle. I will correct the distributor in terms of advance to make sure that the engine runs smooth. And then finally, I'm going to spin up the engine on different RPMs, and I call that the full dynamic adjustment. And then I might readjust my distributor in terms of advance until everything is working smoothly. So now let's look on those individual steps. Assuming that we have breaker points, the first thing we're going to do is to set the gap. That is not very difficult. We'll take off the distributor cap and we're going to rotate the engine until the top of the notch on the shaft inside the distributor is pushing on towards the breaker points and pushes them wide open. So look for that top point on that notch. Once that is done, then you get your gauge, and typically that will be specified for your specific engine. And remember, the gap here is going to influence the dwell angle. Typically that gauge is between 0.6 to 0.7 millimeters. That's kind of a standard, but it could be different for your engine. Then we're going to loosen up the holding screw, and not too much, but just enough. So with a little screwdriver on the side, you can move the points back and forth a bit so we can adjust the gap. So put your gauge in the gap and adjust the breaker points so that the gauge can be removed and inserted easily. So not that it's pushing the points open or that it's squeezing. And then when that is done, we are locking back down the lockdown screw, and then we're going to recheck the gap. This is how simple setting the gap is. But please respect the gap distance, because that is going to have a huge influence on your dwell angle. The static adjustment is pretty simple and straightforward. So we'll remove all the spark plugs so it makes it easier to spin the motor around, because you will have to do this manual. On cylinder number 1, we're making sure that the cylinder is at its end of the compression stroke. So the valves are all closed. If you're not sure about this, then open up the valve cover and check the valve state of cylinder number 1. In that condition, you will see that the crankshaft marking will more or less line up with the markings on the pulley. Try to set the crankshaft mark at 5 degrees before top dead center, as shown in the picture. Now attach the spark plug to the high tension coil or cable of cylinder number 1, and making sure that you hold the plug against the engine ground. Turn on the contact, but do not start the engine yet. Now you loosen up the distributor bolt or nut which is holding the distributor in place, and slowly rotate the distributor in the normal direction of rotation. So you will have to find out for your car what the normal rotation is, counterclockwise or clockwise. Once you've done that, slowly turn back the distributor in the opposite direction until you see the spark. And then we're going to tighten the distributor bolt, and you're done. Your static adjustment is now set. If you want, you can rotate the crankshaft 2 full turns, and you should see the spark occurring at around 5 degrees before top dead center. If you're running breaker points like in the old days, then it's important that the first thing you do under the dynamic checking is the dwell angle. So we're going to measure the dwell angle, and therefore you will need a strobe light. Now the strobe light typically has a plus and a minus connection, which should go to the battery. And then most of the time you will find also a green lead, which needs to go to the negative side of your high tension coil if you're running on a negative ground system. If you're running on a positive ground system, it's going to be just the opposite. With your strobe set to dwell angle, then you start the engine and you will have to measure the dwell angle on the strobe itself. It will be displayed on the display of the strobe. So making sure that the engine is running at idle, and then verify the readout on the strobe. If that readout in degrees is not correct for your specific engine, then most likely your breaker point gap is set wrong and you should redo it. There is no need to attach the pickup clamp of the strobe to one of the high tension leads going to one of the cylinders, because we are not using the flash mode in this moment in time. It is only the dwell angle. The exact method for your strobe light depends a bit on the strobe light that you have. So here is my dynamic adjustment. Obviously we want to do this with the engine warm, and I'm not going to use a tool for that. So we'll start up the engine. I will loosen up slightly the bolt that is holding the distributor in place, and I'll let the engine run on idle. I will listen to and observe the engine. Does it run smoothly? Does it shake a lot? I will also keep an eye on the RPMs. Either I have an RPM meter inside the car and somebody is watching it and reading it out, or I have attached an RPM meter to the car. I now slowly will rotate the distributor in the opposite direction of its normal rotation, meaning I'm giving it more advance. If the RPM increases, I will continue turning it until it stops to increase. I will then adjust the idle screw on the carburetor so that the engine runs back at its normal speed, because otherwise you're going to get the effect of the bob weights. If the RPM did not increase in the previous red steps on the screen, then I'm going to try turning the distributor in the normal direction. Maybe we had way too much advance already, so I'm going to turn that back a bit, and then we repeat the red steps. Now once the RPM is correct, we're going to do it again. I'm going to do the red steps all over again. So we're going to start again with listening to the engine. We keep an eye on the RPM, and I'm going to repeat the slowly rotation of the distributor in the opposite direction of normal rotation. And if the RPM increases, I will continue until it stops again and readjust the idle screw. And you might go through this a couple of times. And once the RPM is actually correct, I will tighten down the distributor. And if so desired, you can check the ignition timing with a strobe light if you want to know exactly how much advance you have given the engine. But this is the old school method that always works. So now let's start with the full dynamic adjustment of the advance, focusing on the bob weights. And therefore we're going to disconnect the vacuum hose. Now there's a lot of debate amongst people all the time. Should you do the adjustment with the vacuum hose or without? Well, the reality is I want to check the advance pattern of the bob weights. And I don't want to do this with the vacuum advance. That's going to be my next test. So I'm going to let the engine warm up. I have disconnected the vacuum hose, and I'm going to connect my strobe light. I will put the clamp on my first cylinder, on the spark lead. I'm going to start up the engine, and I will mark the amount of degrees of advance I have on the strobe light. Now there's two ways of doing this. If your strobe light can use an offset, then that's great. Then you just make sure that the mark on the pulley and the mark on the engine block line up for TDC, and you adjust the dial button on your strobe light until they line up, and then you can read out how many degrees advance you have. If you don't have such a fancy strobe light, then you can just look onto the indication on the pulley. Where is that mark against the engine block and how many degrees? So we're going to record the measured degrees, and then we're going to increase the engine speed in steps of 500 RPMs. And each time we'll measure and record the amount of degrees. Listen very careful to the engine, because if it starts to ping or knock, then you have too much advanced timing, and you should really reduce the static timing slightly or adjust the springs and bob weights to make sure that you don't get this knocking or pinging. Well, we have arrived almost at the final test, which is the full dynamic with vacuum advance. So we make sure that we have the vacuum pipe hooked up. We let the engine warm up. We connect the strobe light just like before. We attach the clamp to the spark plug of cylinder number 1. We start up the engine, and we go in to measure the amount of degrees advance that we have with the strobe light when running on idle. And we should see more degrees because now the vacuum advance is doing its thing, because the butterfly on the carburetor is actually closed. We'll record the measured degrees. Now, instead of increasing the RPMs, I'm going to disconnect the vacuum hose from the distributor. And I will plug the hose with a small bolt. Now when I disconnect it, the ignition advance should decrease on my strobe light. The good thing is, if you have a vacuum pump, you can now connect the vacuum pump to the distributor membrane and then start pulling vacuum according to the vacuum advance curve that you have for your specific distributor, and you should see the advance being increased without having the RPMs of the engine being increased through the bob weights. So the bob weights are not doing their thing here, it's just pure vacuum advance. Quite often the membrane can be broken inside these vacuum advance units, so then even if you pull vacuum, nothing will happen. And that is it basically in terms of adjustment. Of course, you want to take the car now to a real test spin and accelerate fast, cruise and all this, and making sure that it responds properly. So thank you for viewing this first lesson, and I'm looking forward to your comments to see if I need to continue with something like this or not, and give me advice on what needs to change and what is wrong or what is not clear. Thank you for viewing, and I'll see you in my next video. Bye bye.